Next question, the limit extending to 0, 2 sin square x by 2 power log cos x. We have to evaluate limit extending to 0, 2 sin square x by 2 power log cos x. As x tends to 0, we can see cos x tends to 1 and log cos x tends to 0. And as x tends to 0, 2 sin square x by 2 also tends to 0. This is 0 power 0 form. This is 0 power 0 form. Now, whenever we see 2 sin square x by 2, we can recollect it as 1 minus cos x. So, this limit is limit extending to 0, 1 minus cos x whole power log cos x. Let me call log cos x as some t. Let me call log cos x as some t. As x tends to 0, log cos x, which is t, tends to 0. So, this limit can be rewritten in terms of t as limit t tending to 0, 1 minus. If log cos x we call it t, cos x would be e power t. So, this becomes e power t whole power t. Limit t tending to 0, 1 minus e power t whole power t. Let us call this limit L. This is 0 by 0 form, and whenever we need to evaluate 0 by 0 form, take log. Log L would be, log and limit can be interchanged. Limit t tending to 0, log of this expression, log of a power b is b log a. So, this is t log of 1 minus e power t, t log of 1 minus e power t. Now, this is 0 as t tends to 0, this is infinite as t tends to infinite, this is 0 into infinite form, 0 into infinite and indeterminate form. Let us apply L'Hospital rule to evaluate this limit. Before that, limit t tending to 0, let me write this limit as log of 1 minus e power t divided by 1 by t, log of 1 minus e power t divided by 1 by t. Now, it is infinity by infinity form. Applying L'Hospital rule, this limit would be limit t tending to 0, differentiate numerator 1 by 1 minus e power t into derivative of 1 minus e power t minus e power t divided by derivative of 1 by t is minus 1 by t square, minus and minus 1 gets cancelled, 1 by t square goes up, in the numerator becomes t square. Now, you can see as t tends to 0, e power t tends to 1. So, we can write this as 1, 1 into whatever is that same number. T tending to 0, 1 minus e power t divided by t is 1. So, this quantity is 1. Now, as t tends to 0, this expression tends to 0, log L is equal to 0. Log L is equal to 0. From here, we can conclude L is equal to 1. L is equal to 1. This is how systematically we can do this question. Now, instead of doing all this, we could as well come to a conclusion here. We know as t tends to 0, e power t minus 1 is equivalent to t. E power t minus 1 is equivalent to t. So, this quantity we can replace it by minus t. This quantity can be replaced by minus t. Or this entire expression as t tends to 0, this limit would be t tending to 0, t power t, t tending to 0, t power t, and we have evaluated this limit t tending to 0, t power t in the basic discussion, it would be 1. So, we can say L is equal to 1 directly from here. So, answer is L equal to 1. Next question, f of x is equal to x log cos x divided by log of 1 plus x square, x not equal to 0, and 0 when x is equal to 0. Then option A, f is continuous at x equal to 0. Option B, f is discontinuous at x equal to 0. Option C, f is continuous but not differentiable at x equal to 0. Option D, f is differentiable at x equal to 0. So, in this question, we need to discuss continuity and differentiability of the function f of x is equal to x log cos x divided by log of 1 plus x square when x is not equal to 0 and 0 when x is equal to 0. For this function, we need to discuss continuity and differentiability at x equal to 0. Let us start with checking continuity. For continuity at 0, limit extending to 0 f of x needs to be equal to f of 0, which is 0. Limit extending to 0, x log cos x divided by log of 1 plus x square. We need to evaluate this and check if it is equal to 0. If this is 0, then the function is continuous. Now, log of 1 plus x as x tends to 0 is equivalent to x. Log of 1 plus x square as x tends to 0 is equivalent to x square. So, this quantity we can replace it by x square, or you can as well divide log of 1 plus x square divided by x square is 1. So, dividing and multiplying by x square will also give you the same result. 1x now gets cancelled. As x tends to 0, cos x is 1, log cos x is 0, x is 0. This is 0 by 0 form. Let us apply L'Hospital rule. Limit extending to 0. Derivative of log cos x is minus tan x, 1 by cos x into minus sin x. Divide by derivative of x is 1. So, limit extending to 0 minus tan x is 0. So, we can see this limit exists and is equal to 0. So, we can say the function is continuous at x is equal to 0. The function is continuous at x equal to 0. Now, let us check differentiability. For differentiability at 0, limit extending to 0, f of x minus f of 0 divided by x minus 0, this limit, it should exist and it should be finite. This limit should exist and it should be finite. So, let us focus on this limit. X minus 0 is x, f of 0 is 0, f of x when x is not equal to 0 is x log cos x by log of 1 plus x square. X and x gets cancelled. We have limit extending to 0, log cos x divided by, in the previous discussion we saw log of 1 plus x square is equivalent to x square. So, this limit it will be log cos x by x square. This is again 0 by 0 format. Let us apply L'Hospital rule. Limit extending to 0, log cos x, derivative is minus tan x, x square, derivative is 2x, tan x by x as x tends to 0 is 1. So, this limit is minus half. Limit exists and is equal to minus half. So, the function is continuous as well as differentiable at x equal to 0. So, answer is A as well as D. Next question, if f of x is equal to mod log x, then option A, f dash of 1 plus is 1, f dash of 1 minus is minus 1, f dash of 1 is 1, and option D, f dash of 1 is minus 1. So, we need to check whether left hand derivative at 1 is 1 or right hand derivative at 1 is minus 1 or derivative at 1 is 1 or minus 1. For the function f of x is equal to mod log x, we need to check derivative differentiability of f of x at x equal to 1. So for differentiability, let us first evaluate right hand derivative. F dash of 1 right hand derivative plus is limit x tending to 1 plus f of x minus f of 1 divided by x minus 1. F dash of 1 plus is limit x tending to 1 plus f of x minus f of 1 divided by x minus 1, which is limit x tending to 1 plus f of x is mod log x minus f of 1 log 1 is 0, mod 0 is 0 divided by x minus 1. Now when x is slightly greater than 1, log x will be positive. Log 1 is 0, log is an increasing function. When x is greater than 1, log x would be greater than 0. So mod log x can be written as log x. As log x is positive, mod log x can be written as log x. To evaluate this limit, this is the 0 by 0 form. Let us apply L'Hospital rule. This limit will be equal to limit x tending to 1 plus derivative of log x is 1 by x divided by derivative of x is 1. So this limit, it is equal to 1. As x tends to 1, 1 by x is 1. Now let us evaluate left hand derivative at 1. Left hand derivative at any point a is limit x tending to a minus. So here it is 1 minus f of x mod log x minus f of 1 0 divided by x minus 1, which would be x is slightly less than 1, log x is increasing, log 1 is 0, so log x would be less than 0, negative. So mod log x is minus log x divided by x minus 1 limit x tending to 1. This is again a 0 by 0 format. We can apply L'Hospital rule. Derivative of x is 1, derivative of log x is 1 by x. With a minus sign, we have minus 1 by x. So this limit would be minus 1. So we can see the function is not differentiable at 1. Left hand derivative is minus 1, right hand derivative is plus 1. These two being unequal, we can say function is not differentiable at 1. So option A is true, right hand derivative at 1 is 1. Option B is true, left hand derivative at 1 is minus 1. C and D, f dash 1 does not exist because the function is not differentiable. So answer is A and B. Next question, if x plus mod y is equal to 2y, then y as a function of x is option A defined for all x, option B continuous at x equal to 0, option C differentiable for all x, and D dy by dx is equal to 1 by 3 for all x less than 0. Now we are given an implicit relation in terms of x and y. X plus mod y is equal to 2y. There is an implicit relation with us. X plus mod y is equal to 2y. And whenever we need to talk about mod, we need to see whether the quantity inside mod is positive or negative. So let us split the discussion into two cases where y is greater than or equal to 0 and another y is less than 0. If y is greater than or equal to 0, or for y to be greater than or equal to 0, x plus y, it should be equal to 2y, or y and y gets cancelled, y should be equal to x, and y is positive implies x is positive, y is 0 implies x is 0. So for all x greater than or equal to 0, x is equal to y. If we plot the graph of this function, for all xy greater than or equal to 0, x is equal to y. X equal to y, we know it is a straight line passing through origin. So whenever x is greater than or equal to 0, it is a straight line y equal to x. Let us look at the next case where y is less than 0. If y is less than 0, mod y is minus y, then we will have x minus y is equal to 2y, or x equal to 3y. And if y is negative, automatically x will also be negative. So whenever x is negative, y it is given by x by 3. X by 3 is a straight line passing through origin and having slope 1 by 3. So the line will be less steeper than the previous line. So this is how the graph would be. Y equal to x by 3 whenever x is less than 0. Y is equal to x whenever x is greater than or equal to 0. So this is a function which is defined for all x. We can see this function stretches from minus infinity to plus infinity. It is defined for all x. It is continuous function. We can draw the graph of this function without lifting the pen. So it's a continuous function. It is continuous on R, so it will as well be continuous at x equal to 0. Differentiable for all x. You can see a sharp point here. Right hand derivative at this point is 1. Slope of this line is 1. Left hand derivative at this point is 1 by 3. Slope of this line is 1 by 3. These two being unequal, this gives rise to a sharp point at 0. The function is not differentiable at 0. Elsewhere it is differentiable. For x less than 0, dy by dx, whenever x is less than 0, it's a straight line. Dy by dx is constant, slope of this line, which is 1 by 3. So, option A is true. The function is defined for all real x. Option B is true. The function is continuous at x equal to 0. Option C is false. It is not differentiable at x equal to 0. And option D is also true. Whenever x is less than 0, dy by dx is 1 by 3. So answer is A, B, D. Next question. The function y equal to sine inverse of cos x is not differentiable at option A, x equal to pi. Option B, x equal to minus 2 pi. Option C, x equal to 2 pi. Option D, x equal to pi by 2. In this question, we need to discuss differentiability of the function y equal to sine inverse of cos x. This is a very important function, y equal to sine inverse of cos x. And to talk about its differentiability, let us draw a graph of this function. We know cos x is periodic with period pi. Cos x is periodic with period 2 pi. Sine inverse x is an odd function. Sine inverse of cos x will also be periodic with period 2 pi. Composite function. If the inner function is periodic, then any composition of that function will also be periodic. If g of x is periodic, then whatever be f of g of x will also be periodic. So sine inverse of cos x is periodic with period 2 pi. Because it is periodic with period 2 pi, let us draw a graph of this function from x equal to minus pi to x equal to pi, and the same graph will repeat itself. Because of periodicity, we can cut paste the same graph once we plot the graph from minus pi to pi. Cos x is an even function. Cos x is a even function. So any function of an even function will also be an even function. Any function of an even function will also be a even function. So this function is even function. So whatever happens from 0 to pi, same thing will happen from minus pi to 0. There will be symmetry about y-axis. Let us see, when x is 0, cos 0 is 1, sin inverse 1 is pi by 2. Sin inverse 1 is pi by 2. As we gradually increase the values of x, cos x values decrease to become 0 at pi by 2. When x is pi by 2, cos x is 0, and sin inverse of 0 is also 0. So these values, they decrease to become 0 at pi by 2. Then when x is pi, cos x is minus 1, and sin inverse of minus 1 is minus pi by 2. cos of x, we can write it as sine of pi by 2 minus x. Sine 90 minus theta is cos theta. And when x lies between 0 to pi, pi by 2 minus x lies between minus pi by 2 to pi by 2. And whenever theta lies between minus pi by 2 to pi by 2, sine inverse of sine theta would be equal to theta. And to be more informative, it is a by implication. If and only if theta belongs to minus pi by 2 to pi by 2, sine inverse of sine theta will be equal to theta. So whenever we are talking of x between 0 to pi, pi by 2 minus x lies between minus pi by 2 to pi by 2. So y would be equal to pi by 2 minus x, which is a straight line equation with y-intercept of pi by 2 and slope minus 1. So slope of this line would be minus 1. So this is the graph of the function sine inverse of cos x from 0 to pi. And we already discussed this is a even function. So there will be symmetry about y-axis. Graph from minus pi to 0 is image of this graph with respect to y-axis. So just take image of this line with respect to this line. We have the graph from minus pi to 0. Now we have the graph from minus pi to pi. The same graph we need to copy paste it because of the periodic nature of the function. So now we have the entire graph ready. The graph keeps moving this way. Now let us talk about continuity and differentiability of this function. Cos x is continuous, sine inverse is continuous, their composition will be continuous. And graph also says that we can draw the graph of this function without lifting the pen. So the function is continuous on R. And to talk about differentiability, let us see the sharp points. At sharp points the function is not differentiable, and at all other points it is differentiable. So the function is not differentiable at minus pi, function is not differentiable at 0, function is not differentiable at pi, function will not be differentiable at 2 pi, function will not be differentiable at minus 2 pi. So function will not be differentiable at multiples of pi. At all other points function is differentiable. Let us look at the options. The function is not differentiable at option A, pi. This is true. Minus 2 pi is also a multiple of pi. It's true. At x equal to 2 pi, that is also a multiple of pi. So C is also right. And option D, x is equal to pi by 2 is not a multiple of pi. At pi by 2 the function is differentiable and derivative is equal to minus 1. So right answer is A, B and C. Next question, f of x is equal to sine inverse of 2x by 1 plus x square. Then option A, f is derivable for all x with mod x less than 1. Option B, f is not derivable at x equal to 1. Option C, f is not derivable at x equal to minus 1. Option D, f is derivable for all x with x greater than 1. Let us see. We are talking about differentiability of the function. F of x is equal to sine inverse of 2x by 1 plus x square. We are talking about derivability of the function. F of x is equal to sine inverse of 2x by 1 plus x square about 1 and about minus 1. So if you look at the options, we are talking about differentiability of the function in the neighborhood of 1 or minus 1. So let us look at the derivability at 1. The function is always continuous. Sine inverse x is continuous. 2x by 1 plus x square is continuous on R. Sine inverse is continuous in its domain. And 2x by 1 plus x square always lies between minus 1 and 1. So this function is continuous on R. Let us look derivability at 1. Let us evaluate limit extending to 1. F of x minus f of 1 Sin inverse of 2x by 1 plus x square minus sin inverse of f of 1 is replace x with 1, 2 by 2 which is 1, sin inverse of 1 is pi by 2 divided by x minus 1. To evaluate this limit, sin inverse of 2x by 1 plus x square minus pi by 2 divided by x minus 1. Let us apply L'Hospital rule. Limit extending to 1, f of x minus f of 1 divided by x minus 1. This is 0 by 0 format. Derivative of denominator is 1. Derivative of numerator, derivative of sin inverse is 1 by root over 1 minus x square into derivative of 2x by 1 plus x square, 1 plus x square whole square into 2 into 1 plus x square minus 4x square. We have used u by v rule to derive 2x by 1 plus x square. Now let us simplify this. Limit extending to 1, 1 plus x square whole square goes to the numerator, gets cancelled with 1 plus x square. Then in the denominator we are left with 1 plus x square whole square minus 4x square, which is 1 minus x square whole square under root, we are left with 1 minus x square within mod. Root over x square is not x, it is mod x. Then we have 2 into 1 plus x square minus 2x square, 1 minus x square. Then we have cancelled out 1 plus x square, we will be left with 1 more 1 plus x square. As extends to 1, 1 plus x square is 2, we can cancel out this 2 and 1 plus x square. Now question remains, limit extending to 1, 1 minus x square by mod 1 minus x square. So left hand limit, when x is less than 1, x square will be less than 1. So this limit would be 1 and extends to 1 plus x is greater than 1. So x square will be greater than 1. This limit would be minus 1. So the function is not derivable at 1. Similarly, when we look at the derivative at minus 1, working remains the same except for here we have minus 1. Right hand derivative is minus 1, left hand derivative is plus 1. So the function is not derivable at x equal to 1 and function is not derivable at x equal to minus 1 at all other points, that is whenever mod x is less than 1 or whenever mod x is greater than 1, the function is very much differentiable. So option A is true, option B is true, option C is true and also option D is true. Next question, let f of x is equal to integral 0 to x 1 plus mod 1 minus t dt when x is greater than 2 and 5x plus 1 when x is less than or equal to 2. Then we need to see option A, f of x is not continuous at x equal to 2. Option B, f of x is continuous but not differentiable at x equal to 2. Option C, f of x is differentiable everywhere. Option D, the right hand derivative of f of x at x equal to 2 does not exist. So majorly the focus of the question is about continuity and differentiability of the function f of x is equal to integral 0 to x 1 plus mod t minus 1 dt if x is greater than 2 and 5x plus 1 if x is less than or equal to 2 at 2. At x equal to 2, we need to check continuity and differentiability of this function. So let us start with continuity. For continuity, f of 2 should be same as f of 2 minus, should be same as f of 2 plus. F of 2 is, whenever x is 2, function is given by f of 5x plus 1. 5 into 2 plus 1 is 11. F of 2 minus, whenever x is slightly less than 2, whenever x is slightly less than 2. F of x is given by 5x plus 1. So limit extending to 2 minus 5x plus 1 is also 11. F of 2 is same as f of 2 minus. Let us now see f of 2 plus. Right hand limit at 2. Whenever x is greater than 2, that is whenever x is tending to 2 plus, whenever x is greater than 2, f of x is given by integral 0 to x 1 plus mod t minus 1 dt. As x tends to 2 plus, integral 0 to x 1 plus mod t minus 1 dt can be written as integral 0 to 2 1 plus mod t minus 1 dt. Integral of 1 from 0 to 2 is 2. Integral 0 to 2 mod t minus 1, we can split the integral from 0 to 1. Whenever t lies between 0 to 1, mod t minus 1 is 1 minus t, and from 1 to 2, mod t minus 1 would be t minus 1. We can piecewise evaluate the integral, or draw the graph of mod t minus 1. This is how the graph would be, a v becoming 0 at x equal to 1. We are evaluating from 0 to 2. So integral 0 to 2 mod t minus 1 is area of these two triangles. Area of this triangle is half, base is half, height is half, base is 1, height is 1, area would be half, base is 1, height is 1, area would be half. So total area is 1. So f of 2 plus is 3. F of 2 plus is 3. We can see f of 2 is different from f of 2 plus. F of 2 is different from f of 2 plus. That shows discontinuity at x equal to 2. So the function is not continuous at x equal to 2. Option A is true. Option B, function is continuous but not differentiable. This is absolutely false. Option C, function is differentiable everywhere. Because of the discontinuity at 2, the function is not differentiable at 2. So the function cannot be differentiable everywhere. C is also false. The right hand derivative of f of x at x equal to 2. Let us talk about right hand derivative at 2. It's very interesting. F of 2 is 11. F of 2 function value at 2 is 11. And f of 2 plus is 3. Just immediate next point after 2, the function value drops to 3. So this jump from 11 to 3 is happening instantaneously. In the very next moment from 2 to 2 plus, the drop is from 11 to 3. So this happens only when the derivative is infinitely large, and because it is a drop, it should be minus infinite. So when we evaluate the right hand limit at 2, we are bound to get the limit to be minus infinity. That makes the function non-differentiable, and also right hand derivative we say does not exist, because right hand derivative has to be a finite number. We can say this minus infinite, which is the limit, makes right hand derivative does not exist. So answer is A and D. Next question, the function f of x is equal to integral part of x plus half minus integral part of half divided by x whenever x lies between minus 1 and 2 denotes, has discontinuity at option A 0, option B half, option C 1, option D 3 by 2. We need to talk about continuity of the function f of x is equal to integral part of x plus half minus integral part of half is 0, so we need not write it, ignore it, divided by x. We need to talk about continuity of this function at option A 0, option B half, option C 1, and option D 3 by 2. Now observe 0. 0 doesn't fall into domain of the function, denominator cannot be 0. So clearly there is no chance of continuity at 0. So 0 at 0 function is discontinuous. At 0 function is discontinuous. And what kind of a discontinuity is it? Whenever x is in the neighborhood of 0, x plus half will be in the neighborhood of half, and integral part of half is 0. Denominator is tending to 0. Numerator is 0. So 0 by whatever is 0. And once we define f of 0 separately as 0, the function becomes continuous. So this is a removable discontinuity at x equal to 0. Forget that. For now, the function is discontinuous at 0. Look at option B, half. Left hand limit f of 1 by 2 minus whenever x is slightly less than half. Half plus half is 1, and because x is slightly less than half, x plus half will be slightly less than 1. Whenever a number is slightly less than 1, its integral part would be 0. So f of half minus would be 0. And what is f of half plus? X is slightly greater than half. X plus half will be slightly greater than 1. Whenever a number is slightly greater than 1, its integral part is 1. 1 by half, which is 2. Again you can see f of half is different from f of half plus. So left hand limit and right hand limit are different. There is a discontinuity at half. At half, again the function is discontinuous. Let us observe at 1. When x tends to 1, x plus half tends to 3 by 2, which is a non-integer, and integral part of x is continuous at all non-integers. So clearly at C, function will be continuous. Function will be continuous at x equal to 1. And again at D, 3 by 2, 3 by 2 plus half tends to 2. Integral part of 2 minus would be 1, and integral part of 2 plus would be 2. There will be a difference between left hand limit and right hand limit, and function will come out to be discontinuous at x equal to 3 by 2. So function is discontinuous at 0, function is discontinuous at half, function is discontinuous at 3 by 2, and we are asked for discontinuity. So answer is A, B and D. Next question. If f of x is equal to x cube into signum of x, then option A, f is differentiable at x equal to 0. Option B, f is continuous but not differentiable at x equal to 0. Option C, f dash of 0 plus, right hand derivative at 0 should be 0. Option D, f dash of 0 minus is 1. So let us see, f of x is equal to x cube into signum of x. Let us recollect what is signum of x. Signum of x is 1 whenever x is positive. Signum of a function is 1 whenever x is positive, 0 whenever x is 0, and minus 1 whenever x is less than 0. Signum of x is 1 whenever x is greater than 0, 0 when x is equal to 0, and minus 1 whenever x is less than 0. Now, let us look at continuity of f of x at 0. F of 0, signum of 0 is 0 into whatever would be 0. Right hand limit, limit extending to 0 plus f of x is x cube, signum of x whenever x is greater than 0, x is tending to 0 plus x is greater than 0, and whenever x is greater than 0, signum of x is 1. So limit extending to 0, x cube is 0. Limit extending to 0 minus, whenever x is tending to 0 minus, x cube into signum of x. So signum of x is less than 0, so signum of x would be minus 1. So this function is minus x cube. So as x tends to 0 minus x cube would be 0. F of 0 is 0. F of 0 plus is 0. F of 0 minus is 0. So the function is continuous at x equal to 0. Function is continuous at x equal to 0. Let us check the differentiability. Let us check the differentiability. To check differentiability, we need to evaluate limit x tending to 0. We are checking differentiability at x equal to 0. limit extending to 0, f of x, x cube signum of x, minus f of 0 is 0, divided by x. Limit extending to a, f of x minus f of a divided by x minus a. If this limit exists, the function is going to be differentiable. If the limit does not exist, the function will not be differentiable. So x and x gets cancelled. We have x square. As x tends to 0, x square tends to 0. Whether signum x is plus 1 or 0 or minus 1, the product is going to be 0. So irrespective of whether it is right hand derivative or left hand derivative, this limit will be 0. The limit exists and is finite, so the function is differentiable. So function is differentiable and continuous at x equal to 0. Now look at the options. F is differentiable at x equal to 0, absolutely true. Once A is true, B can't be true. C, f dash of 0 plus is 0, true. F dash of 0 minus is 1, absolutely false. So answer is A and C. Next question. G of x be a function defined on closed interval minus 1 to 1. If area of the equilateral triangle with two of its vertices at 0, 0 and x, g of x is root 3 by 4, then find the function. G of x is a function defined on minus 1 to 1. So domain of the function is given to be minus 1 to 1. Area of the equilateral triangle formed with the two of its vertices at 0, 0 and x, g of x, area of this triangle is given to be root 3 by 4. Area of this triangle is given to be root 3 by 4. Now let us assume side of the equilateral triangle to be A. Let us assume side of the equilateral triangle to be A. We know that area of the equilateral triangle is given by root 3 a square by 4. We know area of the equilateral triangle is given by root 3 a square by 4. So A has to be 1. It is given that the area is root 3 by 4. A has to be 1. So distance between these 2 points is 1. That is x square plus g of x whole square under root is equal to 1. Or g of x is plus or minus root over 1 minus x square. And because g of x is a function, there cannot be ambiguity. Either it has to be plus or it has to be minus. And assuming that g of x is a continuous function, then g of x has to be either root over 1 minus x square for all x belonging to minus 1 to 1, or g of x has to be minus root over 1 minus x square for all x belonging to minus 1 to 1. If g of x can be discontinuous, we have infinitely many possibilities of g of x. So among the options, g of x is equal to minus root over 1 minus x square, option C is a possible option, and g of x is equal to root over 1 minus x square, option B is also a possible option. Answer B and C should be true. Next question. The function given by y is equal to mod of mod x minus 1 is differentiable for all real numbers except option A 0, 1, minus 1, option B plus or minus 1, option C 1, option D minus 1. The function given by y is equal to mod of mod x minus 1 is differentiable for what all real numbers. So for this question, let us plot the graph of this function. Mod x. Mod x, we know it is a v becoming 0 at origin. This is how graph of mod x will be. Mod x minus 1, pull the graph of mod x by 1 unit down. So this is how the graph of mod x minus 1 would be. We are pulling the graph of mod x 1 unit downwards. And now mod x minus 1 becomes 0 when x is minus 1 and also when x is 1. On this we are putting mod. On this we are putting mod. So whenever the function is positive, it remains the same, and whenever the function is negative, that is below x axis, it becomes minus of this. So this gets inverted and this is how our function is ZW. Now we have to talk about differentiability of this function. We know the function is not differentiable whenever we have a sharp point. The function is continuous on R. You can draw the graph without lifting the pen, but we can see a sharp point at -1. Left hand derivative is -1, right hand derivative is 1. Left hand derivative is -1, right hand derivative is 1. Left hand derivative is 1, right hand derivative is -1. So the function is not differentiable at -1. Function is not differentiable at 0. Function is not differentiable at 1. Now look at the question very carefully. The function given by y is equal to mod x minus 1, y is equal to mod x minus 1 whole mod is differentiable for all real numbers except, it is given, this is differentiable for all real numbers except 0, 1, minus 1, plus or minus 1, 1 and minus 1. Now if I say answer is D, that means, let me complete my statement, the function y is equal to modulus of mod x minus 1 is differentiable for all numbers except minus 1, for all numbers except minus 1. That says the function is also differentiable at 0. Is it true? No. So D cannot be the option. Again, let me see whether C is the option or not. Let me fill the blank with C. The function y is equal to mod of mod x minus 1 is differentiable for all x except x equal to 1. Is that true? No. C is not the option. The function is differentiable for all real numbers except minus 1 and plus 1. That makes the function differentiable at 0, which is again false. So answer has to be A, 0, 1, minus 1. There is a clear-cut difference between the questions. The function is not differentiable at. If the question had been the function is not differentiable at, then answer will be A, answer will be B, answer will be C, answer will be D, A, B, C, D. But for this question, the function is not differentiable except for these points. It can't be B, C, D, it has to be A. So answer is A alone. Next question. The function f of x is equal to mod x minus 3 whenever x is greater than or equal to 1. X square by 4 minus 3x by 2 plus 13 by 4 whenever x is less than 1 is option A, continuous at x equal to 1, option B, continuous at x equal to 3, C, differentiable at x equal to 1, and D, differentiable at x equal to 3. So for the function f of x, we need to check continuity and differentiability at x equal to 1 and x equal to 3. Let us look at the definition of the function. F of x is mod x minus 3 whenever x is greater than 1 and also when x equal to 1, and x square by 4 minus 3x by 2 plus 13 by 4 whenever x is less than 1. So this is a piecewise defined function. At 1 we are breaking the definition, and at 3 we have mod x minus 3. So we need to check the continuity and differentiability at 1 and 3. At all other points, function is both continuous as well as differentiable. Now in the neighborhood of 3, function is mod x minus 3, and mod x minus 3 we know is continuous but not differentiable at x equal to 3. So function is continuous at x equal to 3, option B is true. Function is not differentiable at 3, so option D is false. Function is continuous at x equal to 3 but not differentiable at x equal to 3. Let us look at function at 1. First let us check the continuity. F of 1, it is given by whenever x is equal to 1, f of x is given by mod x minus 3. Mod of 1 minus 3 is mod minus 2. Mod minus 2 is 2. F of 1 minus, that is left hand limit at 1. Whenever x is less than 1, left hand limit at 1, whenever x is less than 1, f of x is given by this definition. So put x equal to 1 in this. We have 1 by 4 plus 13 by 4, which is 14 by 4, minus 6 by 4, which is 8 by 4, that is 2. Let us also see right hand derivative limit at 1. Let us see right hand limit at 1. Right hand limit at 1, it is given by whenever x is greater than 1, f of x is given by mod x minus 3. Mod x minus 3 in the neighborhood of 1 will be mod 1 minus 3, mod minus 2, which is 2. So all the three, functional value at 1, left hand limit at 1, right hand limit at 1, are all equal to 2. So the function is continuous at x equal to 1. So option A is also true. Now let us check differentiability at 1. Let us check differentiability of the function at 1. For differentiability, actually we should be evaluating limit extending to 1, f of x minus f of 1 divided by x minus 1. To check differentiability at 1, we should actually be evaluating limit extending to 1, f of x minus f of 1 divided by x minus 1. And to know what is f of x, we need to evaluate left hand derivative and right hand derivative separately. But here, because the function is continuous, we already checked continuity at x equal to 1. And also, in the piecewise definition, we are involved with polynomials. Now, we can say left hand derivative at 1 would be same as derivative at left side point at 1, and right hand derivative at 1 would be same as derivative at right side point at 1. Right hand derivative would be same as derivative to the right side at 1. Left hand derivative at 1 would be same as derivative to the left side at 1. Derivative to the right side. Whenever x is greater than 1, f of x is given as mod x minus 3. And in the vicinity of 1, mod x minus 3, mod 1 minus 3 is negative. So in the vicinity of 1, x minus 3 is negative. Mod x minus 3 would be 3 minus x, and derivative of 3 minus x is minus 1. In the neighborhood of 1, whenever x is close to 1, x minus 3 is negative. So mod x minus 3 is 3 minus x, and when you differentiate 3 minus x, we have derivative to be minus 1. Now let us also see left hand derivative at 1. For left hand derivative at 1, whenever x is less than 1, f of x is given by this. Now let us differentiate and put x equal to 1. Differentiate this. 2x square by 4. X square on differentiation, 2x by 4, x by 2. X by 2 at 1 is 1 by 2. 1 by 2 minus derivative of this is 3 by 2. 1 by 2 minus 3 by 2 is minus 1. So left hand derivative is also minus 1. Left hand derivative is minus 1, right hand derivative is minus 1. So we can say the function is differentiable at 1 and derivative is minus 1. So option C is also true, and the answer is A, B, C. Next question, f of x is differentiable function and f of x into g of x is differentiable at x equal to a. It is given that f of x is a differentiable function and f of x into g of x is differentiable at x equal to a. Then option A, g of x must be differentiable at x equal to a. Option B, if g of x is discontinuous, then g of a is equal to 0. Option C, if f of a is not equal to 0, then g of x must be differentiable. Option D, none of this. So we are talking about differentiability of g of x, given that f of x into g of x is differentiable at x equal to 0, at x equal to a, and f of x is differentiable f of x is differentiable at x equal to a, and f of x into g of x is differentiable at x equal to a. We need to talk about differentiability of g of x. Look at option A. G of x must be differentiable at x equal to a. Is it a compulsion? No. Look at it by an example. Let us take limit extending to 0, x square into mod x, x square into mod x. This limit exists and is equal to 0. This limit exists and is equal to 0. So, limit extending to 0, x cube by x also exists and is equal to 0. So, the function f of x is equal to x cube into mod x is differentiable at x equal to 0. The function f of x is equal to x cube into mod x is differentiable at x equal to 0. F of x is differentiable, g of x is not differentiable. We know mod x is not differentiable at x equal to 0. Still, the product is differentiable at x equal to 0. So, for f of x and g of x, the product of f of x and g of x to be differentiable, it is not a compulsion that g of x has to be differentiable. It is still possible when f of x is tending to 0. So, option A is false. If g of x is discontinuous, then f of a has to be 0. That is what option B says. If g of x is discontinuous, then f of x has to be 0. Let us see why. It is given that f of x into g of x is differentiable at x equal to a. Given f of x into g of x is differentiable at x equal to a. So, limit extending to a, f of x into g of x minus f of a into g of a divided by x minus a, it is given that this limit exists. This limit exists. And it is also given that this limit is finite. Only then f of x into g of x will be differentiable at x equal to a. Now, let us assume that f of a is not equal to 0. Let us assume that f of a is not equal to 0 and it is given that g of x is continuous. If g of x is discontinuous, g of x as extends to a, its behavior would be different from g of a. G of x as extends to a behavior would be different from g of a. So, f of x is differentiable. F of x as extends to a would be same as f of a. F of a I can take common. G of x is different from g of a. So, we have this to be limit extending to a, f of a into g of x minus g of a divided by x minus a. If g of x is behaving differently from g of a, the numerator is non-zero whereas the denominator is 0, this limit does not exist or it will be infinitely large. If f of a is non-zero, that is what we have assumed. G of x is given to be different from g of a as extends to a because the function is discontinuous. G of x is given to be discontinuous in option B. Once this is non-zero and this is tending to 0, for this limit to exist, it becomes a compulsion that f of a has to be 0. So, our assumption that f of a is not 0 is false. So, option B is true. If g of x is discontinuous, it will be a compulsion that f of a has to be 0. Let us look at option C. F of a, if it is not 0, then g of x must be differentiable. That is absolutely true. In the previous assumption itself we have seen, if f of a is not 0, then compulsorily limit g of x minus g of a by x minus a should be 0. So, option C is also true. So, once B and C are true, D can't be true. Answer is B and C. Answer is B and C. Next question. If limit tending to infinity a n minus n square plus 1 by n plus 1 is equal to b, a finite number, then a is 1 or 0, option C, b is 1 or d minus 1. So, given that limit n tending to infinity, an minus n square plus 1 divided by n plus 1 is b, a finite number. We need to find the values of a and b. So, let us take the LCM. Limit n tending to infinity, n plus 1 cross multiply an square minus n square plus an minus 1, this is given to be b. As n is infinitely large, if degree of numerator is greater than the degree of denominator, answer would be infinitely large. So, n square coefficient in the numerator should become 0. For the answer to be finite, n square coefficient in the numerator should become 0. So, a minus 1, which is coefficient of n square in the numerator, should become 0. So, a should be equal to 1. And once a is 1, this term vanishes. A is 1. So, we have limit n tending to infinity n minus 1 by n plus 1. We can ignore this minus 1, we can ignore this plus 1, it is 1. So, b is equal to 1. A is 1 and b is 1. So, answer is option A and option C. Next question. Let f of x is equal to sin x by 1 plus mod x. Then f of x is option A, continuous for all x, option B, differentiable at x equal to 0, option C, discontinuous at x equal to 0 and 1, option D, non-differentiable at x equal to 0. We have to talk about continuity and differentiability of the function f of x is equal to sin x by 1 plus mod x. Now observe, sin x is a continuous function, mod x is a continuous function, mod x plus 1 is continuous. So, ratio of two continuous functions is continuous provided denominator is non-zero and 1 plus mod x can never be 0. 1 plus mod x can never be 0. So, this function is continuous on R. This function is continuous on R. So, option A is true and option C can't be true. Option C says discontinuous at x equal to 0 and 1, which is not true. So, now to see among B and D, we need to talk about differentiability of this function at x equal to 0. So, let us check for differentiability. For differentiability at x equal to 0, limit extending to 0, f of x minus f of 0, f of 0 is sin 0 by whatever 0, divided by x minus 0, that is x. This limit should exist and should be finite. For differentiability, this limit should exist and it should be finite. Now we know sin x by x is 1. We can write this limit as limit extending to 0 sin x by x into 1 by 1 plus mod x. As x tends to 0, sin x by x is 1. Mod x is 0. 1 by 1 plus mod x is 1. So, 1 into 1, this is 1. This limit exists and is equal to 1. So, the function is differentiable at x equal to 0. The function is differentiable on R. So, option B is true. That makes it false at D. So, answer is A and B.